What if I told you there was a company that is producing instruments that are useful for qubits throughout different technologies, be it ion traps, be it silicon qubits, or even superconducting qubits. So this company sits at the very heart of the instrumentation. And with that, welcome to another episode of The Hidden Quantum Champions. Welcome to our company review on Swabian instruments. And before we get into it, as always, get yourself something to drink and then let's get ready to jump into their website. So here we are at Swabian Instruments. In the background, we already see one of the instruments, so with a power supply, some USB connector here, and then we see those golden plugs here, which are coaxial connectors for probably signal delivery. It says, game-changing instruments for your digital signals. Swabian Instruments provides versatile solutions for the handling of digital signals. We combine high-performance hardware with flexible software toolkits and connect them with streaming data paths. Our instruments enable you to process and control your digital signals on the fly. And then it says implement faster. So here we have a TimeTacker series and the pulse streamer. So the TimeTacker series says capture digital signals from your application and process them on the fly with Swabian Instruments TimeTacker series. And then the pulse streamer says define complex digital signal patterns for your application with a pulse streamer. I guess this is kind of a pulse generator, so it can generate arbitrary waveform generator. So you can generate arbitrary signals, arbitrary pulses with it, probably up to a very high frequency range that you can then send down, for example, to your superconducting qubit to excite it, to change its state from 1 to 0 or vice versa. And then with the TimeTacker, I guess this is like a signal acquisition engine that you can use to have like very highly time-resolved signal processing. Then it says, what are your biggest challenges in digital control and measurement? Get us involved, and then you can contact them, I guess. And then below here we have some events where they're probably participating. So we see here the SPIE Photonics West in San Francisco next year in 2026. I'm recording this end of 2025, so in December, end of 2025. And then the next one is here, the big APS meeting in Denver, Colorado in March 2026. Besides that, we also have some news section, I think, down here. We see, for example, one PPS monitoring frequency stability analysis and phase noise analysis demonstration at the International Timing and Sync Forum ITSF 2025 and the EQTC 2025 European Quantum Technologies Conference in Copenhagen. So here we already see the company Swabian Instruments is active in the quantum technology space. And in a moment, I guess we will learn why and what they can actually deliver. I mean, we already know they deliver instruments, but how do they actually play a role? Why are they used? We will learn about that, I guess, in a second. And then here we have some referrals about different universities from different places using their technology. So we have the MIT as a US place, the Sapienza University in Rome, as Italian, so European place. We have the University of Melbourne and the University of Bristol, and I guess it goes on here. So there are like even more. There are even more institutions in there. There are also some news here on awards, like for example, truly pioneering and the major innovation advantage achieved by the developers. So Stuttgart Innovations Award 2021, I think it says here, and there is other ones down here as well. Then at the end we also find some contact number here to reach out to, which is a German number. So they're based in Stuttgart or probably close to Stuttgart in Germany, in the region of Swabia, I guess, Schwabenland, because otherwise it would not be Swabian Instruments. Okay, so with that, let's hop into the products real quick. I think that's something that we've already seen before. So here it says advanced timing electronics for your experiments. Then we see the TimeTacker series and the pulse streamer from before. There are also other ones here like the synchronizer. So the Swabian instrument synchronizer enables you to run large-scale applications with up to 160 input channels. And the DLS-CAT. The DLS-CAT is an enhanced particle size measurement solution which exploits multi-angle dynamic light scattering combined with an intelligent intensity spike filtering algorithm. So that's more like an optical instrument, while the other ones are more, let's say, electrical instruments for pulse generation and so on. Let's quickly take a look at the applications, and here we now see really, let's say, the whole quantum coverage that this company actually has. So we see they are active in the quantum optics and photonic space with their solutions. So we see quantum communication as one of the major pillars of quantum technology. It says throughout the applications here, so photon number resolution, PNR, linear optics quantum information, LOQI, intensity interferometry, and then photonic integrated circuits, PICs. Then there's also quantum sensing and material science. So now we come to the quantum sensors, another important pillar of quantum technology. And here it says optically detected magnetic resonance, ODMR, then SLR and LiDAR, and then also quantum dots, QDs. Besides that, there's also life science, which just for the sake of time, we are not going through those now. And then there's also some timing and frequency synchronization here, like frequency stability analysis and phase noise analysis. I will not go through all of these now. I encourage you, if you are interested, to go check them out. But what I will check out now are the quantum communication part, and then later on also something of the quantum sensors. So quantum communication. Here is again the scheme as we know it, right? So we have two parties, Alice and Bob, that are trying to communicate with each other in an encrypted way. Now, thinking about the let's say Shor's algorithm, which is an algorithm that can do prime factorization, our today's communication is not safe against that in the future. So there's this idea of harvest now, decrypt later. So you basically collect all of the encrypted data today, which with today's computer we cannot crack. So even if the computers are scaling up, it will still take more time than the existence of the universe to actually crack those, unless we figure out a secret algorithm that can do it on a classical computer. But today we say these are computationally hard problems. So that's why, as of today, we are safe. But with this idea of the Grover's algorithm, we can then use Shor's algorithm, we can then use quantum computers to crack this. So if I today kind of sneak in here into this classical channel, and I listen to that, I will later on be able to decrypt this. Now, this idea only holds true if the key is much shorter than the message. If you have a random, let's say, a random way to encrypt your message, let's say in one case you add a 1 to the letter, so an A becomes a B, and the next letter you do -1, then of course the key, the encryption key, becomes as long as the message, but with that you can also make it more safe. So the idea of these prime factorization is that you have a big prime number, but it's kind of hard to find the prime factors of this big number, which is only 2 prime factors. But of course, the number is not as big as the message itself. So now, if you, for example, today were to listen to one of these messages, you would just store it on a very, very big supercomputing center, like an NSA kind of infrastructure. Then maybe in the future you could decrypt it, and depending on what type of secret you have that you are listening to, this could still be a very relevant notification. Think, for example, about your bank details. Probably it's not super important, right? If you have a push notification that you need to type, 7, 8, like in a 2-factor authorization, usually this key is only valid for a couple of minutes. So there probably this scheme is not super relevant yet unless somebody has already this computer. But if you have something like a state secret, like a government secret, which should hold over maybe 50 years, 100 years, whatever, then it becomes already critical, right? Because there might be in the future already a quantum computer that could crack this. And this is where the quantum communication comes in. Quantum communication makes use of the property of quantum physics, especially the non-cloning theorem, and thereby makes sure that you can create an encrypted key and you can make sure that nobody can listen to this conversation or nobody can sniff into this key. And basically, you are making use of this principle and use that to kind of decrypt your classical channel. So here you have the classical message. And besides that, you have this quantum channel. It creates like an entangled pair of photons. So an entangled pair of photons, what is that? So photons are light particles. These carry a quantum property called spin. So they point into a specific direction, let's say up for one photon. And then you have another one which might point into a different direction, like down, for example. Or it could be that one is pointing vertical and the other one is pointing horizontal, like this. And now, if you know this, if you know that they are exactly anti-correlated, you could do something like you could have two polarizers, and you could make sure that these two polarizers, they only have two positions, and now you communicate via the classical channel what position you chose, and then you can basically check if the other one kind of saw exactly the opposite signal that you saw, which, yeah, is an indication more or less, is an indication that it kind of worked. And if now somebody would sit in between here, they would retrieve the information, but they cannot just copy it because there's this non-cloning theorem, so they cannot just measure the photon here and create another photon which looks identical and this is being measured here, because it is not identical, and this is something which this other side here will be able to realize by communicating between Alice and Bob. So that's more or less the idea. If you want to know more details how that works, please let me know down in the comments below. I'm happy to also explain that in a bit more detail. But yeah, you have basically this classical channel, you have the quantum channel. The quantum channel uses more or less the non-cloning theorem. Here you have these SNSPDs, so the single photon detectors. We've seen them in a previous company video already, so if you haven't seen that one, make sure to check it out. There's also a playlist with all the Hidden Champions videos. And these are basically detecting the single photons. And then you have this time tagger here and there, which is basically, I guess, used to analyze these photon clicks. So a photon click is when a photon comes in for this detector, right? And then this data is being transmitted to the computer. Here below it explains schematic example of a quantum key distribution setup between two parties, Alice and Bob, using Swabian instruments TimeTackers. Each party has the ability to detect single photons transmitted through the quantum channel in red using superconducting nanowire single photon detectors, SNSPDs. The SNSPD output clicks are digitized at high rates and very low jitter using a TimeTagger X. Then I guess there's some more explanation down here. So a lot of text explaining the exact details. So here's something about what is quantum key distribution. Then it goes into timing electronics required for quantum communication. And finally, there's this part about the Swabian instrument TimeTackers, an advantage solution to QKD. Let's quickly go through this. So quantum communication describes cutting-edge techniques to distribute information using the quantum properties of single photons. One of the most important applications is providing secure channels of communication using a technique known as quantum key distribution. Unlike classical public key cryptography, this is susceptible to the decryption by future quantum computing-based decryption algorithms. QKD offers unconditional security. Thanks to the quantum properties of photons such as polarization and phase, the communication parties can be alerted when an eavesdropper distributes the photon's state. That's what we've discussed before, right? Many quantum communication protocols have been developed, but in the most generalized form, they involve at least two parties, as Bob, who want to exchange information and who can establish both quantum and classical communication channels. Protocols explicitly take into account that an eavesdropper, Eve, may have full access to both channels, but if nevertheless unable to extract the secret key that Alice and Bob are exchanging. The quantum channel typically requires a single photon source at either party or an entangled photon source to which both parties have access. That's what the second case is what I was talking about. Photons can either be transferred by optical fiber through free communication systems or via space using QKD satellites. The performance of the quantum channel is often quantified in terms of the secret key rate, which is limited by channel loss, the rate at which the source can produce single photons in random states, the efficiency of the single photon detectors, and the implemented protocol. Each of these represents significant challenges for real-world applications and the high cost of a single photon generation and detection. The lack of quantum repeaters for long-distance communication, as well as the lack for protocol standardization, prevent the global implementation of QKD despite its enormous potential. This is also all stuff that we've covered in previous series. The quantum repeater is something where currently a lot of research is going into. Also happy to share some more company highlights about this in future videos, right? Let's move on. So quantum communication is closely related to linear optics, quantum information, LOQI, and has many other applications beyond QKD, for example in secure voting, networks for quantum sensors, and the exchange of quantum information between quantum computers. By transferring qubit states between geographically separated quantum computers with high fidelity, quantum communication may enable distributed quantum computation in the future. There was also one video about the Quantum Internet Alliance here in Europe that I've been publishing previously to this one. So if you haven't seen that one, go check it out. There's more information about all of this involved as well. Back to the text. So in practical quantum key distribution protocols, detecting high rates of incoming single photons with precision is crucial. This requires advanced single photon detection and counting capabilities supported. Good. Now we move on to the timing electronics required for quantum communication. So in practical quantum key distribution protocols, detecting high rates of incoming single photons with precision is crucial. This requires advanced single photon detection and counting capabilities supported by robust time-taking hardware. An example of a modern QKD system is shown in Figure 1. Alice and Bob detect photons with superconducting nanowire single photon detectors, SNSPDs, or single photon avalanche diodes, SPADs, both of which have recently seen significant improvements in performance. To match these advancements, time-taking hardware has evolved in parallel with the characteristics of these single photon detectors. Swabian Instruments' TimeTagger offers low noise, high data rates, and precision to fully leverage detector capabilities and maximize the secret key rate. The critical hardware characteristics of a time-to-digital converter required for QKD experiments is 1. The time jitter, so low electronic timing jitter, directly improves measurement resolution and precision. To maintain optimal performance, it is essential to consider the jitter from SNSPDs, typically around a few picoseconds RMS, and ensure that the timing electronics have jitter levels below this threshold. Then the dead time, so minimizing dead time is critical to avoid data loss, particularly in high photon count rate experiments with SNSPDs currently achieving a minimum dead time of around 10 nanoseconds. Swabian Instruments TimeTackers offer significantly shorter dead times ensuring seamless data acquisition even in advanced experimental setups. Then there's the data transfer rate. Higher data transfer rates enable the collection of more photon events within shorter timeframes, boosting the statistical accuracy of measurements. If data transfer rates are insufficient, overflow and data loss can occur. A robust data filtering system, such as the one offered by Swabian Instruments, prevents data loss and ensures efficient data acquisition. Now let's quickly take a step back and kind of digest what we've seen so far. So time jitter, if I understand correctly, refers to how precise your timestamp more or less is. So if you are measuring something that is very short, like these events here, they are in the picoseconds range. So the detector, the SNSPD, we've seen that in a previous video, for a short amount of time loses its superconducting properties and therefore creates this signal. And this is a very, very short signal, very sharp pulse, and you need to be able to kind of hit that and also measure it precisely with the correct timing. And that's, I think, what the time jitter is there for. Also, there's this dead time, so kind of the time that you need to recharge for the next acquisition, and this is around 10 nanoseconds here in this case. So this is, milli, micro, nano, 10 to the minus 9 seconds. So then you can kind of from that calculate back at which frequencies you will end up here of kind of signal acquisition. And this is in a pretty high range. So kilo, mega, gigahertz range, I would roughly say. So that I think is in a good range for this type of data rates that you want to achieve here. And then, there's the data transfer rate, of course. So you need to also get this data out somehow. There's some filtering happening there, which is required so that you don't kind of mess up your data processing. Then it says here additional advantages of high performance timing electronics. So remote synchronization, the ability to find coincidence between the events measured by Alice and Bob, is often crucial to extracting meaningful data. It requires that their measurements share a precisely aligned time base, even if they are separated by many kilometers. Tools like GPS disciplined oscillators, DOS, and the White Rabbit WR protocol enable nanosecond level synchronization over metropolitan distances. Then you have the time bin and phase-based QKD, so accurate timing ensures precise quantum state measurement, enhancing both data rates and signal fidelity. The photon number resolution, so high timing resolution, allows for advanced analysis such as resolving photon numbers based on SNSPDs, SNSPD output pulse rising edge shapes, which depends on the number of detected photons. And then the TimeTagger series also includes software with direct access to TimeTag streams via USB 3, delivering up to 90 megatags per second, bandwidth. Powerful analytics tools, including coincidence detection, correlation measurements, and conditional filtering, help users optimize the systems and achieve the highest possible performance. So, and then down here there are some more arguments about that. So versatile and intuitive software engine, clock synchronization, which we've seen before, the remote synchronization with those protocols that we've seen before, and the high-performing and scalable hardware. So here's again a note on the low time jitter, down to 3 picoseconds. The exceptional channel capacity, so up to 20 channels, seamless expansion, and superior compatibility. And then there are also some application notes provided, as well as customer success stories on those. Let's not stretch it for too long. Take a quick look into the quantum sensing here as well. So quantum dots, I think, are something very interesting. Introduction to quantum dots, QD, and their role as single photon sources. So we've seen before in the quantum communication, you need to be able to create single photons, or you need your single photon source, and a quantum dot could be one of those. And I guess here we can see some more information about that. I see here's the box is somehow covering a little bit the letters. But again, yeah, I think it looks like we have a very precise explanation here. So this is how a quantum dot is created. So basically the size, the confinement size has to be smaller than the Broglie wavelength of the material you're looking at. And then you have this confinement in the dot, and there's some more explanation here how that actually works and how this dot is created. So then there's something about the characterization with timing electronics and signal generators. Here we see a laser that is kind of pumping this quantum dot into the excited state, and then the quantum dot decays back to the ground state and thereby emits a single photon. And you see here the different kind of benchmarks. So one is the brightness, a constant brightness with one photon by the other, the distinguishability, so every photon should be the same, and the purity, you always want to have single photons and not, let's say, wave packages of multiple photons. And I guess it explains how actually the Swabian instruments hardware and of course also software can help you to realize that. It looks like they are controlling on the one side the laser, but then on the other side also the detector side of things, and help you to analyze both like events over time, so you get this lifetime histogram, but also other things like these coincidence counts that are done here when you have this kind of interferometer type of setup for measuring single photon coincidence. Then the final part here goes into the limitations of quantum dot characterization with conventional timing electronics, and then Swabian instruments, TimeTagger, and pulse streamer, an advanced solution for quantum dot characterization. Then it goes on here with the quantum dots, and finally photon number resolution for single photon source SPS characterization, as well as some, I guess, application notes down here or additional resources and references. So you see there's also resources linked here. You see there's a lot of information available about these different types of applications, and I mean there are even more applications listed down here, so I think there's a lot of things to learn. One, of course, is the entry-level material into the matter, into the subject matter, but then also in terms of understanding how the instruments can actually be interesting for your lab, for your type of setup that you're looking into. There's a whole knowledge base with additional scientific papers and publications linked here, open source projects, I guess, from the community or what they have created for the community. There's also something here about the careers as per usual, and then finally there's something about the company as well. So here we can now see, so the headquarter is in Germany, in Stuttgart, but there is also a Boston office here, as well as a Shanghai office that they have available. In the About section it says, Swabian Instruments is a test and measurement company headquartered in Stuttgart, Germany. We develop and sell digital data acquisition and signal generation systems that are easy to use, performant, and packed with useful features. Our instruments empower scientists around the globe to perform groundbreaking research. With our TimeTacker series, we are emerging as a technology leader in time-correlated single-photon counting instrumentation. We are growing and founder-led company. Mission statement: we strive to make data acquisition and signal generation as easy and intuitive as possible. We enable scientists to implement their research ideas with just a few lines of code and help them maximize the time they spend on their actual research. We put lots of thoughts into our systems architectures and the interface that the user interacts with, and shift the boundary of what is possible with modern data acquisition and signal generation systems. Roots: Swabian Instruments was founded in 2016 by Helmut Feder, Michael Schleckmüller, and Markus Wick, with the goal to commercializing the new TimeTagger technology that the team had developed at the University of Stuttgart. The founders had worked together on novel instrumentation for single photon counting that they needed for their research. They had designed instrumentation that satisfied the demanding requirements posed by single photon quantum physics applications. At the same time, the new system was easy to use. The new team members were able to work with it efficiently from day one. The first TimeTacker quickly became known within the research community worldwide and sparked the foundation of Swabian Instruments. And then here's the history. So 2016 is the funding with the spin-off and an Exist scholarship in Germany, all the way towards 2019 by parallelizing tapped delay lines. Swabian Instruments demonstrates a record-breaking time resolution with FPGA-based time-to-digital converters of 2.7 picoseconds RMS jitter. After complementing his PhD in electrical engineering, Markus Wick joins Swabian Instruments as a shareholder and CTO. Swabian Instruments moves out of its university startup garage to a new location in Stuttgart-Zuffenhausen, which is actually quite a famous place for technology in Stuttgart or around Stuttgart. Swabian Instruments is a top 3 finalist of the Deutsche Gründerpreis, Germany's most prestigious entrepreneur award. And here we see, I guess, the founders and some information about them as well. So looks like they all have a very solid technical background from what I see down here. And then, of course, there are also some more information on projects that they are involved in. Here you also see the Quantum Internet Alliance I was talking about before, as well as the Q-Link X, IQST, and Q.Tech, and then Synphos, okay, as well. And then there are also some partners down here. So you see Single Quantum, for example, but also Photech and other ones as well. Then we see again the awards and some news at the lower part. With that, I'm actually happy to come to an end of today's video. I hope you liked it. If you don't want to miss out on the next one, make sure to subscribe to this channel. And as always, stay hydrated and see you in the next one. Bye bye.